Okay, so we are very happy to have Pawel Caputa today, who is at Warsaw University now, and he has been working on the fundamental understanding of the AdS CFT conjecture and many other very interesting problems, and he's going to talk about his work on path integral optimization and seeing AdS CFT in this language today. So over to Pawel. Let's hear from you.
Okay, so thank you very much, Ian, for the invitation and giving me the opportunity to speak. I would love to be in Chennai now, but unfortunately, this has to wait a bit. So yes, I'm going to talk about path integral optimization from CFT to AdS. This is some, oh, sorry, can you see my cursor now?
Yes, it is.
Okay, great. So this is some older work, but I'll talk about, I'll give a short introduction and motivation behind this works that we have been doing. And then I'll describe the so-called path integral optimization. And in the second part of my talk, I'll discuss recent updates on this from the holographic side using Hartle-Hawking wave functions. And then I'll conclude and discuss some open questions. So please stop me at any time. And if, as I understood, it's quite flexible, so we can also discuss afterwards. And I can go into more technical details if somebody is interested, or so don't hesitate to stop. And as I said, this is based on somehow already quite an old work. So we started this developments in 2017 with the group in Kyoto of Tadashi Takayanagi and Masamichi Miyagi and Kento Watanabe that were students at that time, and also with Nilai Kundu that is now faculty at IIT Kanpur. And then the second part of my talk will be based on the very recent update done together with my student Jan Boruch at the University of Warsaw. And also I'll talk about work that will appear very soon on arXiv with Jan and also my postdoc Dongsheng and Tadashi. Okay, so let me start with the very general but somehow a brief motivation for why are we doing this. So as you probably all know by now, we have this amazing approach to quantum gravity given by the AdS CFT correspondence, where CFT, certain quantum mechanical, certain very special quantum mechanical systems are exactly equivalent to string theory or gravity on an anti-de Sitter spacetime. And in some generic, we know many, of course, technical and very precise examples of this duality. But generically, we have this relation between quantum states of CFT, say vacuum or thermal state, or some more complicated quantum states of this quantum mechanical system, being somehow dual to different spacetimes, different geometries in asymptotically AdS geometries. For example, vacuum, we know it's dual to empty space, thermal state is dual to some geometry where there's a black hole, and so on and so forth. And we can compute very detailed computations of, say, correlation functions or entanglement entropies on both sides of the correspondence. And using the holographic dictionary, we can actually compare them and check that they match. So for my purpose, I'll be thinking about this duality as some duality between states and geometries. Sorry. On the other hand, states in quantum field theories, and in particular also in CFTs, they are defined by Feynman path integral, where basically we take some Euclidean action of a CFT with all the quantum fields specified by this curly phi. We impose a certain boundary condition on the Euclidean plane for this. I just denote all these collective fields collectively this way. We impose a boundary condition, and then we perform the path integral over all possible configurations of fields with this boundary condition for phi 0 of x. And then this defines for us a wave functional, actually in quantum field theories, that is a functional of this boundary condition. So somehow this description of state is actually equivalent to any other ones. In holographic CFT should capture or hide the information about AdS geometries. And the big question of our program is how can we extract this information? How can we extract this geometric structure of anti-de Sitter spacetime from path integrals in conformal or in holographic conformal field theories? So this is the motivation. And then somehow, in order to make progress in this direction, we are very inspired by the idea of tensor network, or in other words, in the idea of extracting geometry from tensor networks. This idea in the context of AdS CFT usually is dubbed as AdS tensor network, and that dates back to the works of Giefer, Vidal, and Brian Swingle, that noticed the following interesting resemblance between the tensor networks and holographic geometries. Namely, tensor networks are usually very useful tools in many body systems to represent states, in particular to represent many body wave functions. And usually in tensor networks, I'll be interested in particular in the tensor networks that describe conformal field theories or critical points of many body systems. We decide on particular tensors that we're going to use in approximation of the system, and then we put them in particular so-called tensor network together, such that these endpoints of the tensor network describe physical degrees of freedom, whereas the way we connect the tensors and the way we somehow do particular approximations and contractions, that represents for us not the exact wave function, but actually an approximate one that still captures a lot of useful information about particular CFT state. So in particular, in this Mera tensor network, after we optimize this, after we choose particular tensors and then decide on the particular algorithm, after optimization, these tensor networks look like some kind of discrete versions of geometry. And Brian Swingle noticed that actually they very much resemble slices of AdS spacetimes. And one of the strong, or actually supporting argument was that the famous Ryutake-Yanagi prescription for entanglement entropy of some subregion of AdS, of some subregion of the CFT that is computed by geodesic that goes into the bulk, in this tensor network is also resembled by some minimal cut through the network, which is actually an upper bound on entanglement entropy of some subregion of degrees of freedom in this wave function. So this very interesting observation led to the so-called AdS tensor network developments, and somehow led to a new paradigm that maybe the geometry of holographic geometry may be hidden somehow inside states of CFTs, the same way, or in the same way as it's kind of hidden in tensor network as basically some emergent geometry after the optimization that also actually that somehow captures the structure of entanglement. The important thing about this tensor network, so-called Mera, is that when we do this optimization and also somehow representation of a quantum state of a CFT, we really take into account the structure of entanglement. Once we optimize the state, we remove some local entanglement between the degrees of freedom. So this is, and only in that tensor network, basically we can notice this resemblance, at least according to Brian. So in my talk, this is still a motivation and somehow kind of general idea. But with this idea or with this motivation, we would like to now kind of move back to our original setup, namely holographic CFT, and try to see if we can use any of this, many body or tensor network language, like optimization, like representation of states, and so on and so forth, but really working somehow generalizing it to large and interacting conformal field theories. So in other words, we would like to turn this observation about some geometry of AdS CFT as emerging from some kind of continuous tensor network into a tool in AdS CFT correspondence. So in other words, we want to come back to the representation of wave functions or quantum states in CFTs by this path integral with fixed boundary conditions with Euclidean action of a CFT, and ask these tensor network-like questions. How can we actually optimize these states? And then how can we extract geometry from these path integrals the same way as we were observing some geometry from this tensor network? And finally, there was a further motivation that we were really strongly trying to develop, namely how to quantify complexity of the states. Even though this will not be so much a part of my today's talk, it will come as a product of this development. Okay, so is the motivation and questions that I want to address clear at this point?
Yeah. Could I ask for a clarification, please?
Yes, please.
Yeah, in this path integral, the phi's are being integrated on the tau equal to 0 slice. Do you mean that, or is it for some?
Oh, sorry. Thanks for
tau less than negative?
So here I'm doing the path integral in this Euclidean action over, say, for the vacuum over a whole Euclidean plane, and I'm just imposing the boundary condition for the quantum fields at the Euclidean tau equals to 0.
But
so,
you are not, for example, if I take 2D CFT in the usual radial quantization, then I would integrate inside the unit sphere and put the boundary unit disk and put the boundary condition on the circle, and that would be give me a wave function.
Exactly, this is what I'm doing here.
So you have to integrate on some half space in this.
I will be integrating over half space. Also, I will be integrating over circle right there, and then here I'm just imposing the boundary condition at tau equals to 0.
Yeah, you need to put the boundary condition, which will define the wave function, of course. Yeah.
Exactly.
So okay, thanks.
But the functional integral is over the whole plane or disk or something. Thank you for this clarification.
Thank you.
Okay, great. So, trying to generalize these ideas from tensor networks to really genuine quantum field theories, we came up with this idea of path integral optimization. And this is done as follows. So, the original path integral that prepares for you, say, a vacuum of a CFT or actually any QFT, is done on the Euclidean plane, say, for the Euclidean time from -infinity to 0, or for convenience, we can set it to some epsilon that represents the UV cutoff of the original theory. And then this path integral, we can think about it as some original tensor network that prepares a state where at each kind of small plaquette of this path integration, we have to do the same amount of path integration at each point of this, say, Euclidean flat lattice. And then in order to somehow approximate a state while keeping its properties intact, we decided to actually come up with some kind of tensor network prescription like for the path integral, namely by fixing the boundary condition at the Euclidean time tau equals to -epsilon to be the same as in the original path integration. But instead, while going towards the Euclidean time tau, we decided to, in this prescription, we actually do less and less somehow we do some coarse graining procedure where at each step we do somehow less path integration in such a way that, with this fixed boundary condition, we still prepare the same quantum state, but in somehow on a different, with somehow less and less numerical, you can think about it as numerical path integrations. And since we are working in the continuum limit, we can think about this procedure of going from this original flat lattice to somehow a coarse-grained lattice by simply introducing the metric G on the Euclidean path integral. And then this step from the original to the approximate path integral, in some sense, this will describe for us this continuous tensor network that then we'll think about that we'll think about some as a version of a continuous tensor network. And then after having done this, we need to give you a prescription for some kind of an optimization of this tensor network path integral that will pick for you with this fixed boundary condition, in some sense, the optimal metric G on which this path integral will be prepared in the most efficient way. So the second part of this approach from tensor network, namely the optimization, was designed in such a way that we compare the wave function prepared in this original Euclidean space with this fixed boundary condition here to the path integral in the new metric G with the same fixed boundary condition here, such that we really prepare the same state. And then we take the ratio of those two wave functions, namely wave function computed with this metric G and wave function with flat, and we define this as exponent of some functional action G, as some functional action I that is a functional of this metric G that we then minimize in such a way that the minimal value of this functional I of psi of G picks for you with this fixed boundary condition, selects for you the optimal metric. And this action I psi of G, we call this a path integral complexity action that tells us basically how complex was the preparation of this state using this path integral on metric G. I'll elaborate on this more, but this is a setup for like that. This is a generalization of this idea of tensor networks to the CFT path integral optimization. And then the minimal of this action then at this particular, so the value of this on-shell action at this particular minimal metric G is defined as a complexity of the state psi prepared by this path integral. That's the prescription.
Pawel?
Yes.
I have two simple questions. The first question is this hyperbolic space that you're talking of is still in time, right? There is no extra dimension here.
Yes. Thank you for that. So this is very important here. Everything, all the geometries that I'll be talking about, they are geometries on the space where I'm doing Euclidean path integral. So actually, I didn't mention. We'll see that after this optimization, we'll actually find that these metrics that we're gonna get here are hyperbolic metrics, in the same way as the metrics that were observed to be like in the connection to the Mera tensor network. But one should really keep in mind that everything here, at least in the first part of my talk, will be in the Euclidean time tau.
Yes, so you do not have an extra dimension emergence yet from this story.
At least not in the first part of my talk.
Not in the first part. So the second question is that, so usually the way we understand complexity is like some kind of norm, some kind of a distance measure. But
this is important. This will not be a distance measure here.
Yeah, it doesn't seem like, yeah.
So, okay, so given a tensor network, there's and once you tell me like what kind of tensors you're going to use, and you give me the optimal tensor network, there's a natural way of thinking about its complexity as roughly the number of tensors that you really needed to use to prepare a particular state. And then this notion here is like a continuous version of this one. So you can of the same. So you can think about these tensor networks as you will see this action, on-shell action will be roughly proportional to the volume of the space. So you can think about this as basically a number of these continuous tensor networks that you are using here. And in order for that to be true, we need to have a condition that basically each of these plaquettes contributes the same way to the path integration. And indeed, we have this condition that basically the integral over this Weil factor that we'll have here is fixed to be particular. It's fixed to 1 or fixed to epsilon squared, depends how you normalize. And this allows us to give us this allows us for interpreting this volume of this space as basically a number of these continuous tensors used to prepare a state. But I will tell you in a few slides, this will be a relative measure of complexity in a sense that it will compare basically, say, particular state with another state. And this will not be a distance measure in a sense that it can be also negative. I will come back to that.
But is there something like this that if you go from say 1 to 2 and 2 to 3, then going from 1 to 3 would be less complex than the sum of these two, or there's nothing like
okay,
that?
that's okay. I'll give me maybe 2 slides or 3 slides, and I'll come back to that. Okay. So let's be very.
Could I make a comment, please? Yeah.
Yes, please.
In your case, the second figure is probably just a representative figure of the kind of graphs that you consider. Is that correct? But
you mean here?
Yeah, the second figure, yes, the one in the middle.
Yeah, it's some graph. It's just some generic graph of this type.
Yeah, but it's actually very curious that this graph is the graph associated with a class of groups called Baumschlag-Schlachter group, which has 2 generators A and B, and in this particular case, it's given by A, B square, A inverse equal to B. But in general, it will be A, B to the power M, A inverse equal to B to the power M. And the graph that you get is, if you follow a loop, you can see what I mean. The vertical lines are A, say, then you go A, then 2 short lines that's B square. Then you come back down by A inverse. That's equivalent to B inverse in this case, which is the same as B in this particular case. But in general, you could have more graphs of this type. And I don't know whether that helps in doing any calculation or using some results from there. So these are a class of groups which were discussed by Baumschlag and Schlachter. Whereas the flat space graph, that's of course generated by A and B, which commute. AB equal to BA.
Oh, I see. That sounds very interesting. I didn't know about this, so I would love to hear more.
You can just
Indeed,
Google it.
In my case, it's more like some generic graph that anyway I'll be working in the continuum limit, but I think this is also very interesting to know that the one can actually write this, because by this I will mean some kind of hyperbolic space. So I would
so these are discrete versions of hyperbolic spaces. These graphs are.
I see. Very interesting. Thank you for that. Maybe I can ask you later for some references.
Sure.
Okay, so let's be very concrete and go and try to do this in 2-dimensional conformal field theories, where basically any metric that we can put on this 2-dimensional Euclidean plane can be written basically as a Weil factor of this field phi of tau and x, and then some reference metric g hat AB. This is 2-dimensional. In most of my talk, I'll be actually using this GAB to be flat, but at least for these slides, I'll keep it general. And actually, to get this, to derive what's the action in the ratio of 2-wave functions, you can just go back to your first courses on string theory, or actually to this seminal work of Polyakov, where basically we know that the measure of the path integral in CFT in the Weil rescaled metric g hat AB times e to the 2 phi transforms in a way that is proportional to the measure in the reference metric AB, and the proportionality factor is nothing but exponent of the famous Liouville action that is a functional of this Weil factor and also depends on this g hat. So this is the full Liouville action, where we have kinetic term, the famous Liouville potential. Usually we have also coupling to the background for non-trivial g hat metric. In my talk, this will be 0. And also sometimes you might need also the boundary Liouville terms. What is great about this action is that this is very universal in a sense that it only depends on the central charge. And so in a sense, it's in a universality class of entanglement entropy of a single interval that is proportional to C, and is the same for any 2-dimensional conformal field theory. And in particular, we can take C to infinity to hope to match with some holograph. And also another important factor here is the coefficient of the potential, which is usually referred to as a Liouville cosmological constant. And this we can actually obtain, we can usually shift the field phi clearly by some constant to reabsorb it. And sometimes we can just, in our actually first paper, we can set it to 1. But in the second part of my talk, it will actually play some role. The mu will play some important role. Okay, so in 2-dimensional conformal field theories, we have this universal result for the ratio of the wave function, or in other words, for our path integral complexity, given by the Liouville action. And notice actually that this there's actually not just a Liouville action, but it's a Liouville action where from the Liouville action in phi, we also subtract the volume where we have, sorry, we subtract the term where we have phi set to 0. This is the this is general from the definition of the measure in a CFT. And in fact, okay. Okay, so I will discuss, one should bear in mind that that this action in some sense will depend on two things. It will depend on somehow metric G1, which is basically some reference metric times the value rescaled one, and then the reference metric itself, some kind of action that has basically two metrics as its entries. Okay, so the optimization then that I told you here, basically the optimization of this functional or choosing the minimal value of this functional for a given choice of the metric corresponds to nothing but solving the Liouville equation of motion from the Liouville action, which in general is given by this equation. And actually it's equivalent to the constraint that the Ricci scalar of the metric that we are talking about, the full metric G. So this full metric G, which is value rescaled and the reference one, should be constant negative. So in this setup, usually we set mu to be positive. So in other words, the optimal backgrounds from this procedure are hyperbolic. They have constant negative curvature. So for example, maybe the formula that you are familiar with is the one for the flat background, where we have the famous Liouville equation with d and d bar on some complex coordinate tau plus ix that we define as w. So the Liouville equation is given by this, and this will give us the optimization constraint for our factors. And then this constraint that I told you that we have to fix the same boundary condition on this, we have to do the same amount of path integration in this general metric G as we have to do with in the original space. This is actually guaranteed by choosing the boundary at the Euclidean time equals to 0 or minus epsilon that this Weil factor goes as 1 over epsilon squared. So we really match the original cutoff, UV cutoff of CFT. Okay, so let me do these examples very quickly. We can do it for particular states of 2D CFTs. For example, for the vacuum, we have to do this path integral on upper half plane. And then the right solution of Liouville equation with correct boundary condition is the hyperbolic one, H2, where again, this tau is not, this tau is nothing but the Euclidean time. And at tau equals to epsilon, it satisfies the boundary condition that goes as 1 over epsilon squared. And indeed, as in the tensor network, you can think about it as formally as a slice of AdS geometry, as a time slice of AdS geometry. But as Ian pointed out, you would have to do this formal identification between time and radial direction. And I'll go back to this, to the holographic interpretation of this metric in the second part. So bear with me. At least this kind of resemblance of holographic slices at this moment is not is just some curious observation. And actually, this observation goes also to more complicated states. So if we do this path integral optimization on the strip of size beta over 2 that prepares for us the thermophile double state, we again get the right solution that has the correct boundary conditions on two sides. And again, if we replace tau with z, we would actually reproduce the time slice of the eternal black hole in AdS3. Similarly, if we do this for path integral on the cylinder with some operator primary insertions, for example, we can find the solution that describes the time slice of conical singularities in AdS3 after replacing tau with z. And actually, we also did this analysis
Ion, we can hear.
No, we can hear him.
Sorry. Okay, maybe my connection. Sorry. Apologies.
Okay. Yeah, thanks. Let me know if something goes wrong, then I can repeat. Okay, good. So we also check that for perturbations of the CFT, we get geometries that resemble time slices of AdS-free process scalar field. And we could also generalize it for arbitrary background jihad that is relevant for the so-called inhomogeneous CFT. Okay, so let me, this will not be so important in my talk, but let me actually, sorry, the complexity itself will not be so important in my talk, but since there were already questions about this in some comments, so let me just discuss some properties of this path integral complexity action. That is basically the minimum of this action computed in some background metric jihad versus some metric jihad times the value scaled form. In general, you can think about this as relative complexity between two metrics, G1 and G2. And actually, this is also this comes from the property of this effective action that we get from the transformation of the measure, that this action is anti-symmetric in a sense that if we compute it between G1 and G2, it's minus the action computed between G2 and G1. And again, as I was referring, it's more like the number of tensors. So let's say if we have some tensor network with 100 or 150 tensors, then it's clear that it can be negative depending on with respect to which number how I'm subtracting the numbers. But also the interesting property of this action is that if we take three metrics, say G1, G2, and G3 that are related by these Weil factors, then the sum of the actions between G1 and G2 and G2 and G3 is nothing but just the action between G1 and G3. So this triangle, actually this action satisfies the triangle equality and not inequality. And as I was pointing, because of this negativity, actually this action, because of action can that could be negative, you should think about this action as a relative path integral complexity, but it should not be thought as complexity based on the distance measure, because by definition, this distance measures, they cannot be negative.
Pawel, can I ask you something? How general is this statement? Because suppose if you introduce, so now you're computing the vacuum in an arbitrary metric, but suppose if you insert operators now in your path integral, when you do it, will this equality will still hold?
Yeah, so with this primaries, actually here, this primaries that we use here, this is not just a vacuum, and also thermofield double is not just a vacuum, it still holds. So this is just a property of this this so-called co-cycle property of this action that appears in the transformation of the measure here. And all the solutions will have such properties.
Okay, so at least even in introduce primary operators that have good transformation properties.
Yes. Yes.
Okay, thanks.
Yeah, thanks. So okay, so I was trying to argue that I mean, as a potential complexity action, it has interesting properties. So for example, minimization of this complexity action leads to the equations of motion of gravity, actually, or it gives us slices of AdS spacetimes in the tau coordinates. It gives us, at least for universal states, it gives us generic volume scaling of this path integral complexity action. And it's very universal because it's proportional to the C only. It doesn't care about so many details of, at least for some simple states, or so many details of your conformal field types.
Actually, also, can I ask something again? So
yes.
How do you know which slice to take? This slice itself is not a gauge invariant notion, right?
So how do we take this line?
Yes, because on its own, it is not a gauge invariant notion.
Yes. So you're asking how are we interpreting the slices from?
Yes, yes, indeed.
Okay, so I think this is again some question for the second part of my talk. So please bear with me.
Sorry. Okay, you're going to come.
Okay. Great. And And then also there was some intuitive interpretation in terms of tensor network like MERA of the Liouville action itself, that some terms correspond to particular tensors in the MERA like unitaries, and some others correspond to some isometries. I'll not go into that, but you can think about Liouville also in this way. It guided us how to define complexity for some universal for some universal setups of 2D CFTs using so-called energy momentum gates, where basically we could think about complexity geometrically a la Nielsen, but using based on Virasoro symmetry. So actually, this work with Javier was very much motivated by the Liouville action properties. I will also not have so much time to talk about. And also Tadashi was arguing generally that one should be able to generalize this prescription for more general spacetimes. And in particular, one could think about tensor like slices of AdS geometries as just as some kind of tensor networks of path integrals on this slices, and they would not need to be Euclidean, but general Lorentzian spacetime with arbitrary time-dependent slices. And that was his proposal of the paper from 2018. Again, I will not have too much time to talk about it, but there has been also many other developments of this path integral complexity up to date. Instead, sorry, how much time do I have?
Well, if we go by 1 hour, then you have
20 minutes or something.
20, yeah, 25 minutes, because we started.
Okay. Yeah. Okay, great. So then maybe I'm just going to briefly mention some generalization of this one. So actually, we also try to generalize this path integral optimization action to higher dimensions, and in some sense, it was a phenomenological generalization, in a sense that basically we wanted the action that had the same properties as Liouville. For example, this cocycle property that I was discussing, or triangle equality, that would also lead to constant curvature solutions as basically the solutions of optimization that would match with the anomalies, for example, in even dimensions for the sphere and computation of entanglement entropy. I didn't have time to describe how we compute entanglement entropy from this Liouville approach, but this is also in our longer paper. And given that somehow set of constraints and phenomenological consistency check, we came up with this action that again describes the relative complexity between some background metric G hat and e to the 2 phi times G hat. That somehow, after many trial and errors and fixing coefficients, this is what we came up with. So there's again a potential, there is a coupling to the R, and there's a kinetic term. And this coefficient n we fixed by matching with the anomalies for the sphere. But actually, after some time, we also realized that this action can be written in a better way. Namely, if you again choose the metric to be basically some Weyl rescaled metric times some arbitrary factor G hat AB, this is in D dimensions, you can write this action as nothing but the Einstein-Hilbert action itself of this metric. But it's important that this should be Einstein-Hilbert action in D dimension with AdS cosmological constant in D dimension. Mu is this arbitrary parameter here. This is just a simple exercise to check that this action, once we plug this metric, reproduces exactly this one. After also we integrate by parts. And if you write it in this form, actually this is obvious that the variation with respect to phi leads to nothing but the trace of Einstein's equations, because it's just a Weyl factor. So it's not the full Einstein equation, but just its trace. And you know, of course, that the trace of Einstein, sorry, can you hear me? I just got some notification that my internet is unstable.
Yes, we can hear you.
Okay. So basically the variation of this action with respect to phi is nothing but the trace of Einstein equation, which is again the constant Ricci scalar constraint for this continuous tensor network. So this generalizes the Liouville equation from 2D to higher dimensions, but to the so-called Diknerovich equation. And also in lower dimensions, we showed that actually this path integral optimization action can be naturally written in terms of Schwarzian action. Okay, so this has been the state of the art until very recently. And I'm gonna discuss now how can we think about this procedure, this path integral optimization, in the context of AdS CFT correspondence, or in other words, what is the gravity dual of this procedure? Up to now, I showed you some universal properties and somehow a curious resemblance between this Euclidean time and some slices of AdS, but I would like to make this more precise in the following part of my talk. But before I go there, maybe are there any questions to the first part? Okay. So are you with me?
Yes, no problem.
Okay, okay, great. So before I move to the second part of my talk, actually, let me just do a brief review of one concept that's probably for many of you is familiar, but in case you are more like quantum information theorists or people doing not playing with gravity, maybe this is not so natural. So I'm gonna in the remaining part of my talk, I'll be using a lot the notion of the so-called Hartle-Hawking wave functions, which are nothing but, again, the generalization of wave functions, definition of wave function using Euclidean action from field theory that I was talking about in the first part. And in their work, they actually describe a Euclidean path integral in gravity in order to prepare a so-called wave function of the universe. So the same way as we do the wave function or wave function in the field theory by simply choosing the boundary condition on our field and doing the path integral over all configurations of the fields with this particular boundary condition, Hartle and Hawking proposed to define the wave functional or wave function of the universe, where on some constant time slice, in their case, they chose the induced metric Hij, and then they would take the Euclidean action, namely Einstein-Hilbert plus Gibbons-Hawking, and then with this fixed boundary condition on the slice, they would do the Euclidean path integral that would prepare this wave function. And so this is a natural generalization from field theory. And then the equation for this wave function, or like generalization of Schrödinger equation, is obtained by basically taking the classical Hamiltonian constraint, so of gravity, that you're familiar, and rewriting this in terms of canonical momenta Pij, and then in some sense quantizing doing canonical quantization by replacing Pij with derivative with respect to the metric, such that the wave function then satisfies the so-called Wheeler-DeWitt equation, differential equation for this wave function. Okay, so this is just a recap, and in the rest of my talk, this Hartle-Hawking wave functions will be important, but more in the AdS context, where we are not thinking about time slice, but rather as a radial slice, as it is natural in AdS CFT.
Pawel, since this is probably going to be important for your talk, so can I ask what happened to the other momentum constraints here? How do you take care of them?
Oh, so they basically they are important momentum constraint, but they tell you that it should not depend on the choice of particular slice and so on and so forth. So the equation for the wave function is basically just the Hamiltonian constraint, but the other momentum is also important, but it doesn't provide a differential equation for the wave function.
Yeah, but it's probably if you are going to some kind of subspace, then this doesn't matter probably, because if you choose some specific kind of slicing, I don't know, maybe you're fixing some gauge where this becomes trivial.
Exactly.
Or
so it should not depend on the particular gauge.
Okay.
Great. This will not be so important, but indeed you're okay. So great. So now I want to present for you this kind of new idea that we came up with recently, and where we try to describe this path integral optimization in the dual AdS geometry. And namely, we wanted to understand, basically, let me just stress this again. We wanted to understand this optimization as well, this action that is an action of two metrics, of some reference one and the value scale one, from the perspective of AdS. Yeah. So this is our setup. Basically, we start with some AdS geometry. Here I'm just drawing AdS free, but we can do it for arbitrary dimensions. And we consider a region of space denoted as M between the usual boundary of AdS. So this is asymptotic boundary. Here on the axis, I have the usual Z coordinate of Poincare AdS, and this is tau here denotes the usual Euclidean time of AdS. I have a boundary sigma at Z equals to epsilon. That's one part of the region. And the second part of the region is the surface Q that is defined by a function Z as a function of Euclidean time. And this surface, basically this surface is somewhere in the bulk of AdS3. And on this surface, I'm introducing coordinate V or W that goes between W equals to 0 at the surface, at this boundary at Z equals to epsilon, and then up to Z equals to minus infinity into the box. So it's just some negative coordinate W. And in this region M, I'm now computing the Hartle-Hawking wave function. So as I told you, the wave function is computed by imposing a boundary condition on this, on some slice. In my case, it will be a slice Q, and then doing the path integral in gravity with all the possible, so with Einstein-Hilbert action, with all the possible configurations with this fixed boundary condition.
Sorry, what is the boundary condition again? So you choose some arbitrary slice, but then you put a Dirichlet boundary condition there.
So I will fix the induced metric on this.
You fix the induced metric as well as
in Hartle-Hawking case. I will fix the induced metric, and then I will perform the path integral over all possible configurations. The novel thing about AdS is that actually, you know, the work of Hartle and Hawking, it was actually in de Sitter or flat space. In AdS, of course, the wave function, this Hartle-Hawking wave function has an extra ingredient, namely the boundary of AdS sigma. So implicitly, we actually also impose the boundary condition for the metrics on the asymptotic boundary sigma. And we will impose in such a way that the metric, that it's basically the usual asymptotic boundary condition, that the metric is just, that corresponds to the vacuum AdS free, so that the metric goes as 1 over epsilon squared at the boundary. And the boundary condition, so the boundary condition that we impose on the surface Q is given by this following metrics, basically, that are related by the Weil factor e to the 2 phi to the flat metric on the surface Q, where this Weil factor e to the 2 phi is defined, is actually given as 1 over this function, this embedding function f of tau. In order to do that, of course, we have to introduce this coordinate W that puts the induced metric in this form, but I will show this explicitly in the example. And the boundary condition for this metric, as I told you, should be such that we meet as we go to this W equals to 0, which is basically here. This Weil factor should be the same as for the surface sigma, which is 1 over epsilon squared. So this is our prescription in the gravity. Are there any
Pawel, this condition e to the power phi is f inverse. This comes from that that it should be the induced metric, or?
Yes. Okay, this will be clear in the example, I hope.
But this is sort of a, I mean, beyond there is no generic motivation from the Hartle-Hawking wave function itself to impose this condition, no?
No, so this is just a way of defining surface Q. Okay, so as I showed, basically we start with, okay, let me just maybe it's good to repeat this. So we start with the Poincare metric, for example, in AdS3, and we define the surface Q as basically surface where Z is equal to this function f of tau, and I'm claiming that this function f is general. Okay. This is some general embedding function f of tau. And I'm claiming that we can always put the metric on this surface Q. If we take it, in AdS Poincaré at least, we can always put it in the form e to the 2 phi times the Weil rescale, like e to the 2 phi times the Weil flat, e to the 2 phi times the flat metric, where e to the 2 phi is given by 1 over f square of this metric, of this embedding function f.
Okay, thanks. But I don't see how this is generally possible because for 2 dimensions, maybe this is true if it's a 2-dimensional surface, but if it is a higher dimensional surface.
Yeah, this is very important point. So actually, again, in 2 dimensions or in AdS3, all the surfaces by uniformization, they will be possible to be written in this way. That's exactly true. In higher dimensions, not all the surfaces can be written this way, indeed, because in in general you can choose more general embedding functions and so on, and there will be and rewriting it in the Weil flat form will not be possible. So in higher dimensions, our ansatz for the metric on Q will be a restricted ansatz for only a class of the metrics that only a class of surface Q that we are interested in. I have not actually discussed this in detail, but in fact, in higher dimensions, when we propose this action here, we are also considering the same ansatz, that basically we take the Weil rescaling of the metric. We take the metric on the surface, like basically here, to be in the Weil flat form, but in most of the cases we were taking in higher dimensions G to be flat. So again, in higher dimensions, this was only an ansatz for some restricted class of metrics. I will show you that actually also you can see it in our upcoming paper, that for all the there are many interesting solutions that fall into this class, but indeed more general metrics maybe require some extra treatment. But by extra treatment, I don't mean anything fancy. Actually, you could impose the metric on Q arbitrarily, and then you would need to solve Einstein's equations for such a spacetime with this particular boundary condition, so for arbitrary metrics. But for Weil flat, it's particularly simple to solve. So that's just the only technical assumption.
Thank you.
Okay. There's also a very important factor in our construction, namely the tension term. So we'll consider this generalized Hartle-Hawking wave functions, where on the top of Einstein-Hilbert action and Gibbons-Hawking, I will also add the tension term to the surface Q. This will be actually extremely important in our story, but I'll go back into this. So here, this action T stands for the tension. Okay, so of course, in general, to compute this wave function is, of course, beyond what we know about quantum gravity at the moment. But as in Hartle and Hawking, we can actually evaluate this wave function semi-classically by simply taking evaluate this action on shell, where the action, computing wave function as exponent of minus the on shell action on the geometry with this particular boundary condition. And in this on-shell computation, I just need to take the Einstein-Hilbert action and Gibbons-Hawking term, and this is the tension term that we add on the surface Q. So this is a prescription just for the Hartle-Hawking wave function between these 2 boundaries. In general, one boundary where I impose some reference metric G1, and then another boundary where I have another metric that is G2 that is related by Weil rescaling to the metric sigma 1. So already from this, maybe you can see some resemblance with the construction of this relative complexity action, but that's where I'm heading. But now I need to tell you what is the equivalent procedure on the gravity side of the optimization path integral of the path integral. And we claim that this is actually the maximization of the Hartle-Hawking wave function with the prescribed boundary condition with respect to this Weil factor phi. It's natural to actually think about maximization when you think about computation of correlation functions, like in gravity, for example. You will know that they'll be given by its expectation value, and in the saddle point approximation, of course, we need to maximize over the choice of this Hartle-Hawking wave function. And actually, in our setup, once we have this tension term here, this maximization now is equivalent to the boundary condition, the Neumann boundary condition on the surface Q. So basically, this is the full Neumann boundary condition that actually also appears often in this so-called AdS BCFT construction. And this is the trace of the Neumann boundary condition that basically tells you that this extrinsic curvature of the surface Q is proportional to the tension. So in other words, the surfaces in the bulk Q that maximize this Hartle-Hawking wave function, they will be given by the so-called constant mean curvature slices of AdS. Okay, so before I go to an explicit example, here is our proposal. We claim that this maximal metric on Q, or this prescribed reference metric on sigma, is you should think about it as a gravity dual of the metric from the path integral optimization that we are obtaining on the field theory side. That's point one. Point two is that we should think about this gravitational action in this region M, including the Hayward term, because actually we are dealing with the corner here, as basically playing the role of our complexity or path integral complexity functional, but not just the one in the CFT, but the one with finite cutoff corrections. And I'll describe what I mean by that. And in particular, we can show that this action in the region M exactly satisfies the same properties as the path integral complexity on field theory. So for example, if we take some metric G1, if we define it for some surfaces Q1 and Q2 with metrics G1 and G2, then it's anti-symmetric and satisfy the co-cycle property. And moreover, the claim is that the minimal value of the action, at least for the Euclidean cases, will be given by the tension T equals to 0. Okay, so that's the prescription. Are there any questions about this before I go to the example? Okay, so let me discuss the example. So for example, in the vacuum, as I was telling you, we start with Poincare metric in D dimension. And then this region M is given by the range of Z coordinate between epsilon, this is the boundary cutoff where the sigma lives, and the function f of tau. Once we do this, we can introduce this coordinate W in such a way that we rewrite the metric in the Weil-Flat form, and then we evaluate the action on shell in D dimensions. And actually, this action in D dimensions, like Einstein-Hilbert, Gibbons-Hawking, and the tension term on Q, can be written in a very nice and closed form, where basically this is the divergence coming from this metric on sigma in this example. And then the part that describes the metric on phi, or that depends on this Weil factor phi, is given by this G as dot phi, so some square root, and then there's some arc sine, and there's a tension. So what I was describing here, that in the previous slide, that this action is the same as the field theory action or the path integral complexity with finite cutoff correction. Basically is captured by this formula, namely if we expand this action in the UV limit, where basically this the derivative of the field phi is very small, we actually precisely recover from this action our path integral our conjectured path integral complexity action for arbitrary dimensions D in this mini superspace approximation where the field only depends on tau, because I took some homogeneous slice in this case. So, but the full action in the gravity is given by this. So it has all the finite cutoff corrections in it. And when I'm computing the saddle point with respect to phi, you can check that variation leads to the equation that the extrinsic curvature on Q is proportional to T. And so, in other words, that this should be the constant mean curvature slice. And we can solve this equation again with this Weil factor e to the 2 phi given by L square over 1 minus T square over D minus 1 times W square. So actually, as we get a family of solutions that that are now basically interpolating between T going to -1 and where basically actually here. So we get a family of solutions. Basically, these are surfaces Q that interpolate between T being to minus D minus 1 over L in D dimensions and T going to 0, where the internal angle is given by the sine over theta. And then when we evaluate this complexity action, so basically the gravity action with the Hayward term, that's very important, this action is minimized for the value of t equals to 0. So basically the slices that we are considering, or this maximization of the Hartle-Hawking wave function, basically gives us the surfaces between here and here. And then this complexity of the surfaces is the minimal one for the slice t going to 0. So actually t, yeah, for the surface t equals to 0. Actually, we can do similar examples for excited states. So for example, in AdS3, if we take the BTZ geometry, again, we can run through the same procedure. We can find equations from the action to be proportional to the tension. And the solution in this case are exactly given by the same ones as we were getting from the path integral optimization in this coordinate W now. And we can check that they are the ones that are they are the family of slices between the boundary. This is basically a half cigar of BTZ between the boundary at t equals to -1 and the slice at t equals to 0. That is actually the minimal slice. And this is exactly the slice for t equal to 0 that reproduces for us the optimal path integral geometry that we got previously. Actually, this class of solutions gives us other solutions, also these conical singularities by analytic continuation RH to I alpha. And we can actually in the upcoming paper, you can check that we can generalize this result for higher dimensional black holes, JT gravity, as well as the Lorentzian geometries. Okay, so maybe let me just, before I conclude, I wanted to present one slide that gives you somehow a gravity perspective on what we are doing, because recall that I was telling you that the slices that we are getting on the field theory side, so basically both on the gravity side, both in the Liouville in the 2 dimensions as well as in higher dimensions, there were slices of constant Ricci scalar. Whereas here I'm claiming that we are getting like our equations of motion, or this maximization gives us the constant mean curvature slices. So how is this compatible? Well, namely when we compute this Hartle-Hawking wave function, we start with some, we compute them in the geometries that solve Einstein's equations in d+1 dimensions. So let's say Poincare AdS or this BTZ. And so we can just take this Einstein equation and now consider our slice Q with some normal vector n mu. And basically, if we now dot this Einstein's equation with this n mu and nu, with these 2 vectors, we are deriving nothing but the Hamiltonian constraint. Okay, so this is this Hamiltonian that any slice of the solution of Einstein's equations, of course, by definition, should satisfy. But as I told you, the maximization of Hartle-Hawking wave function actually gives us the Neumann boundary condition on Q. So Neumann boundary condition on Q was basically that Kij is proportional to the induced metric, as I was showing you here. So this is the Neumann boundary condition and its trace. So actually you can show that that this combination that appears on the left-hand side of the Hamiltonian constraint, namely k² minus Kij, this is nothing but the constant, again, proportional to this tension. And if we just plug it back to the Hamiltonian constraint, we are exactly reproducing that the Ricci scalar of our surface Q should be constant, because this is just a cosmological constant. So in other words, basically from Hamiltonian constraint and our maximization of Hartle-Hawking wave function, we are getting that the Ricci scalar should be proportional to this cosmological constant with 1 minus the tension over d-1 square. Whereas if we compute, if we compare the Ricci scalar from the path integral optimization that I was just showing you from the action, we had basically this potential of the Liouville being mu. We have a dictionary between our surfaces on the gravity side and on the field theory side for mu being non-identity and t being to non-zero as well in this following form. Of course, for mu equals to 1, as we did in the previous paper, and t equals to 0, this is, of course, our previous dictionary, but with the replacement of tau with the coordinate, with the radial direction h0. But
Pawel, can I ask something here?
Yes.
So one of the things that you discussed in the first part of your talk was that this Liouville action was universal. It doesn't matter what the field content is, right?
Yes.
But when I talk about this gravity picture, I mean, the dual gravity we know for the CFT will have other fields too. And
yes.
is it obvious that these results are that universal?
Yeah, no, that's an excellent point. So actually, indeed, when we on the CFT side, we included some fields. For example, we can deform our CFT by some operators that should correspond to some fields in the bulk. Okay, and in that case, when we will be solving Einstein's equations in the bulk, of course, it will not be just pure gravity. Here, I just took the pure gravity. So the stress tensor here is just proportional to the cosmological constant. In that case, if I really wanted to consider other fields on the top of just universal sector of a CFT, on the top of just a stress tensor, let's say, I would need to consider basically more general T mu nu here, and then I would need to solve the a Hamiltonian constraint with not just the cosmological constant but with T mu nu. So actually, the gravity procedure is very, very clear, and it can be done with arbitrary fields in the bulk. Whereas recovering this from field theory may take a bit longer, in a sense that, I mean, in principle, it's clear what to do, but maybe more non-trivial examples would even the deformations that we did was a bit complicated. So I think the field theory procedure seems a bit more complicated, but at least in principle, it's clear what to do for more fields.
Is there some non-trivial check that one can do in that case? I mean, so here the check seems to be constrained by very similar structures of hyperbolic geometry, but somehow one would like to see if one could make it a bit more non-trivial.
Well, yeah. So on the field theory side, yeah, I think this on the field theory side, this computation that we did here, where we had perturbations of the CFT with some scalar field in the bulk, this we could solve in perturbation theory. One could try to match this with the gravity setup. That would be something non-trivial beyond the pure gravity in the bulk. Yeah,
you just said that you introduced a conical singularity already. It's like you basically using the heavy operator.
Oh yeah, for conical or for heavy operators, this works perfectly. We also have done this in the paper.
Yes, but for more non-trivial thing, I think you have to go beyond pure gravity, right? I mean, this is
that's right.
Yeah,
that's right. So in fact, this is something what we are also exploring with Shumit Das and Deep Tarka. That is in the audience, where we can basically study this for the collapsing shell of matter or things like that in the bulk, where you have non-trivial time dependence on both sides.
Mm-hmm. Interesting.
But it's still some work in progress. Okay, so great. So basically, I just, beyond that comment, I would like to discuss, well, I would like to just mention two things. So one thing I already told you at the start, when we take this gravity action that describes the surface Q, namely this Q to define times this function G, and then we expand it in the UV limit, we are again reproducing the boundary path integral complexity action in D dimension, where this field only depends on the coordinate W. So for the homogeneous setup, it's that action in the mini superspace, so approximation. That's one comment. The second one is that indeed, like the tension, like from this prescription I told you on the gravity, the tension of the brane plays the role of the Liouville cosmological constant. And we are interpreting this as basically in some units of, say, epsilon, this cosmological constant basically being equal to 1 is the most optimal or the maximal solution that corresponds to t equals to 0. But actually, we can think about all these non-trivial mu slices between 0 and 1 that correspond to difference on the boundary side that simply correspond to the bulk slices with non-trivial tension t not being 0. So I was showing you that the tension in the bulk goes between, say, d minus 1 and 0. And all these slices, we propose to interpret them as tensor networks again, but not the optimal ones. So basically, this is the the most not optimal, and this is the optimal one. And all the tensor networks as slices of this bulk between here and here are kind of suboptimal with respect to this t equals to 0. And finally, well, this is maybe something for discussion. We can actually write this matrix on this AdS matrix, exactly this matrix here. We can write them as basically a class of metrics of this type, where we basically integrate, where we add some part of the metric in terms of mu, or equivalently some part of the metric with respect to t. And actually, this matrix, you can check that they solve AdS equations of motion. In other words, that you can think about this parameter mu, or the tension, as basically some time that emerges from tensor networks, in a way that, well, that basically by considering different time slices of the bulk corresponds basically to doing different cost graining with different UV cutoff on the boundary side. So that's also, maybe this is something more of a discussion, but it's an interesting observation from this bulk analysis. Okay, so I think I'm over time, and so let me just conclude. In this talk, I wanted to describe for you the path integral optimization method that somehow started from this interesting observation in free theories and in tensor networks and so on. And then we've been working for already some years to promote it and to develop it into an exact tool in AdS CFT. And from this tool, we want to extract the geometry of the bulk from CFT states. As a byproduct, but actually a very important one, we derive a universal formula for complexity, for path integral complexity in two-dimensional and higher dimensional conformal field theories that is universal and applicable to many states using path integrals. From the gravity, I try to argue that this path integral optimization procedure is equivalent to maximization of Hartle-Hawking wave functions with these two boundary conditions, the same as we have the path integral optimization action as a functional of two metrics. Here on the gravity, it's a metric on sigma and on Q. And that path integral geometries correspond to the constant mean curvature slices on AdS spacetime. In particular, with my collaborators Onkar Parikar and Yorit Kuturov, we actually gave another interpretation of these slices of the bulk in terms of the TT bar construction. So we explicitly constructed the time-dependent TT bar deformations that takes the CFT on the slices. I didn't have time to talk about it, but it's an interesting connection as well. And finally, I finished with this observation about tension, or this Liouville potential as an emergent time from tensor networks. This is something very interesting that we are exploring, and it would be nice to understand its precise role to the connection to the so-called York time, where York time is basically defined in terms of the extrinsic curvature, constant extrinsic curvature, that by our equation of motion is again proportional to the tension. But this is something still we're thinking about. And finally, it would be very interesting to understand better the Lorentzian setups, where we have non-trivial dynamics in the bulk in terms of some fields, and generalize this prescription, say, to really holographic models like n equals 4 super Young-Mills, where in principle, the path integral is well-defined and the bulk is well-defined. So, you know, the computation is more of a technical one, but it's definitely something that we are thinking about. Okay. That's all. Thank you for staying with me, and sorry for going over time.
Thanks for this great talk, Pawel.
Thanks.
Yeah. So let's take some questions from the audience.
Yeah, I have a question. I did not see any tensor networks in your construction. And how did you say at the end that these families are like tensor networks?
Maybe you were late at the talk.
No, you had only a schematic in the beginning.
Okay, okay. Good,
but
good.
I mean, after that, I saw nothing.
Oh, very good, very good. So that was the important point, that somehow we were really motivated by this idea of tensor networks and like Mera geometry, and basically bulk geometry as emerging from some geometry of tensor network that prepares states in CFTs. But the important point of my talk was that, or all this works, is that we wanted to generalize this ideas from tensor networks like optimization and preparation of state and extracting geometry to really continuum quantum field theories and preferably strongly interacting large and CFTs. So unfortunately, let's say MERA or tensor networks of this type for CFTs, they can only be constructed for some non-interacting theories, or maybe in some perturbation theory also for interacting ones. But this is not the class of models I was interested in. That's why I didn't really talk about specifics of these models. But I wanted to think about this as this Liouville action and the geometry of the Liouville action itself as a continuous version of tensor networks for CFTs.
Thank you.
Does this answer?
Yes, I mean, but somehow I was hoping to see something discrete emerge, you know. That's what I was expecting. But do you think there is a possibility of kind of partial discretization of the Z coordinate?
Actually, yeah, this is very interesting. This is a very interesting question. So in fact, one could actually take our prescription really seriously for the tensor network community and really try to do this numerically. Let's say take some, even in some free models, and try to discretize a space and put it on a hyperbolic space and so on and so forth. And this I think nobody has done really numerically yet, but actually people like Jens Eisert and Alex Jan and I think Zoltan Zimboras, they looked at some classes, so-called match-gate tensor networks, and then they noticed that actually if they do these tensor networks not on the flat space, not using say flat tiling but hyperbolic tiling like you would have to do in our prescription, actually it was much more efficient to prepare states or to get states numerically this way. So, so in fact, there has been some works that are somehow vaguely related to this concept of putting tensor network, like putting the path integral on the hyperbolic space and extracting a tensor network for CFT from it. But I think it would be interesting to do it, like say numerically in some say free boson or free fermion CFT.
Thank you.
Yeah, actually, I have a very fundamental question, like Suresh. So this tensor network is not really a path integral, right? I mean, tensor network is something else. It's like a multi-scale wavelet transform, if you want to put it that way, or something of a state. So I don't see a natural connection between path integrals and tensor network. Yeah, actually, so yeah, that's also a good point. I didn't have much time to talk about it, but indeed, there has been a very interesting series of works by Ashley Milstead and Gifre Vidal, where they, after our works on this path integral optimization, putting different geometries, they actually they studied this very carefully and considered different path integrals in CFT on different geometries. And in that approach, they were able to derive a circuit that would, that they were able to show that each geometry, different geometry on which you would perform the path integral, would give you sort of MERA-like quantum circuit that would be preparing for you the state. And in their construction, they indeed show that they can start with hyperbolic space or de Sitter space, or actually some null sheets of AdS or DS. And indeed, from these different geometries, they derive different kind of circuits or different tensor networks that prepare for you states in conformal field theories. And in particular, they argue that actually MERA tensor network does not correspond to a slice of AdS or DS, as it was actually debated for a long time. But they were arguing that actually MERA corresponds to a light-like sheet of AdS. And in fact, we also have some interesting comments in our approach about this. So for example, if we do our optimization for Lorentzian AdS or DS, we can derive similar, like we can exactly obtain some surfaces of this type, basically some Hartle-Hawking between for some time-like or space-like slices in AdS. And indeed, in our optimization procedure, we see that for time-like geometries, the optimal geometry is actually, of course, it's not the one on the boundary that was the least optimal, but the optimal geometry is the one that ends on the null sheet. So this is exactly like
the path integral geometry of Giffre and Ashley that would prepare for you the Mera network. So answering your question maybe more concretely, indeed, there's a connection between putting a metric, computing a path integral or partition function, say, on different geometry and the tensor network itself. And this is this work by Giffre and Ashley that was very explicit about this.
And the usual Mera is a light leg sheet on AdS. That's this.
Yeah, that's their claim. Yes.
Huh. Very good. Okay, so more questions then? You can at least have one more. Okay, so people, we actually had another talk before your talk, so today was a long day. So thanks again, Pawel, for this great talk.
My pleasure.
And hope to see you in Chennai sometime.
Hope so too. Thanks a lot.
Okay, so goodbye, Pawel. Goodbye, everybody. Have a nice day, all of you.
Bye.